Hello guys, this is CodeNCode and this is 25th lecture for the number theory course series. And as we have been studying non-deterministic primality test algorithm, we are going to extend it by this lecture. So in this lecture we are going to study and implement and also solve a problem using Fermat's primality test, which by the way tests whether the given number is prime or not in log n time, of course with certain probability of error. Now, Fermat's primality test, as the name suggests, is a method or algorithm to test whether the given number n is prime or not, with of course some error probability of error. Now, Fermat's primality test is completely based on Fermat's little theorem, and that is where the name came from. Now, Fermat's little theorem says that for a prime number p, a raised to the power p minus 1 is congruent to 1 modulo p. This is what Fermat's little theorem says. The source for this lecture is going to be cpalgorithms.com and Wikipedia. The link of both I'll be putting in the description so that you can go and read more about this. Now, Fermat's little theorem says that if p is prime number, then a raised to the power p minus 1 is congruent to 1. This equation generally doesn't hold for composite number. Pay attention to the word in general. Now, in general, this equation does not hold for composite number, and that is what we are going to use to test whether the given number p is prime or not. Now, what we'll do to test whether the given number p is prime or not, we'll be selecting a base a, which will be from 2 to p minus 2. And then we'll calculate a raised to the power p minus 1 modulo p. Now, in most of the websites where you are going to study and where you will be studying this primality test, they don't tell you why we choose a in the range 2 to p minus 2. Why don't we go till p minus 1? I'll be telling you that in a moment. First, let's concentrate on the algorithm, how we'll be doing this. So first of all, you'll choose a base a, which will be from 2 to p minus 2. And then you'll be calculating a raised to the power p minus 1, which is basically this, a raised to the power p minus 1 modulo p. Now, if the result, basically a raised to the power p minus 1 modulo p is not equal to 1, then we are 100% sure that this number p is not a prime number, because Fermat's little theorem says that if p is prime, then a raised to the power p minus 1 is going to be, a raised to the power p minus 1 modulo p is going to be 1. But since the result is not equal to 1, that means this number p is not a prime, but it is actually a composite number. So this we are 100% sure. So if result is not equal to minus 1, then base a is known as Fermat's witness, and the prime number p is actually a composite number. So a would be known as Fermat's witness for compositeness of p. So basically here we are 100% sure that the given number p is not a prime. But the problem arises when the result is equals to 1, because there are some composite numbers as well for which a raised to the power p minus 1 is congruent to 1. Oh yeah, one important thing, the Fermat's little theorem says that a raised to the power p minus 1 is congruent to 1 modulo p, where a and p should be co-prime with each other as well. Basically, GCD of a comma p should be equal to 1, or they should not share any prime divisor. That was one important thing, and this you might already know, just to make sure. Now, if the result is actually equal to 1, what we are going to do? The number p is actually known as probable prime, because p can and cannot be, it is possible that p is prime, and it is also possible that p is not prime. So here we are not sure when the result is equals to 1, because there are some composite number for which a raised to the power p minus 1 is congruent to 1 for every a, that is for every base which is co-prime to p, and those are special kind of number I'll be telling you in a moment. Now here we are not 100% sure, and that is why p is known as probable prime. Now what can we do in this case? See, usually most of the primes, usually the composite number, it is very unlikely that for random chosen a, it is going to generate a, when you calculate a raised to power p minus 1 modulo p, it is going to give you 1 each time if you perform this test in 4 or 5 iterations. So it is very unlikely that you are going to get 1 every time if p is actually a composite number. So what we do actually, if I show you on the CP algorithms, oh sorry, I put, just a second, let me show you the primality test. And here, Fermat theorem is very unlikely that when you see, if you get it is not equal to 1, it is 100% sure that the given number n is actually composite number, and that is why we are returning false from here. Let me just increase the font size. Yeah, but when it is equal to 1, if n is actually a composite number, it is not going to have it is very unlikely that each time when you perform, we'll be performing the test again and again this many times. We'll choose number of iteration, how many times we are going to perform the test if the result is equals to 1. If n is actually a composite number, this is very rare that in each iteration it is going to result into 1. In one of the tests it is going to result into not equal to 1 if it is a composite number, and that is why we run the test for certain iteration to reduce the probability of error. And that is what is happening here. So what we will be doing, if the result is equals to 1, we will be running it 5 or 10 number of times, these many for these many iteration. You can choose it yourself. The more iteration you perform, the better the results are. Basically it reduces the probability of error. So what is happening here, first of all we'll be testing for less than 4. If the number is less than 4, then if it is 2 or 3, then it is prime, otherwise not. So that is what we are taking care of here. After that we are running the test for these many iteration, whatever you define. Each time we'll be generating a random number a in the range 2 to p minus 2. I still haven't told you why we go for p minus 2, why don't we go for p minus 1. I'll be telling you that in a moment. So we choose a in the range 2 to p minus 2. This generates random number, take modulo with n minus 3, and this whole expression gives you random number in the range 2 to p minus 2. Now you generate a raised to power n minus 1 modulo n. If this is not equal to 1, if the result is not equal to minus 1, then in that case we are 100% sure that the result, the given number n is actually a composite number. That is why we are returning false. False means it is not a prime number. Otherwise, if it is equals to 1, then we are going for the next iteration. And after running for all of the iteration, if in all of the iteration it is returning 1, that means it is very highly likely that the given number n is actually a prime number, and that is why we are returning true here. Now bin power is actually a function that uses binary exponentiation to calculate a raised to power n in log n time. So here it is a probable prime, and we will run a test for as many iteration as possible, as in fact we define. Generally it is 5 to 10. The more iteration you perform, the better the results are. So that is what we'll be doing. And the question is why we choose a from 2 to p minus 2. Why don't we go till p minus 1? The answer is very simple. See, if you are calculating a raised to power n modulo p, then a raised to power p modulo a raised to power n modulo p is equals to a modulo p raised to power n, and finally you can take modulo again. So if you choose a to be p minus 1, p minus 1 modulo p is equals to minus 1. If p is odd, then p minus 1 would be even, and a is converted to minus 1. Minus 1 raised to power even is going to be 1. So if p is odd and composite number like 21, if you choose a to be p minus 1, then a raised to power p minus 1 is going to result into 1, and that is why we don't go for p minus 1, but we go till p minus 2. and this is also stated on the Wikipedia page that I'll be providing the link with, so you can go and read there as well. That is the same reason why we don't choose a to be 1. Now, as I told you, there are some numbers which may cause difficulties for us, and those numbers are known as Carmichael numbers. So first of all, let us study about Fermat liar and Fermat pseudo-prime. If P is composite number, if the given input is actually composite number, but still after choosing certain A, the base, the Fermat test tells you that basically the Fermat's little theorem holds for certain A. If given number P is actually composite, then the base A is known as Fermat liar, and number P is known as Fermat pseudo-prime. Nothing important here, just certain little theoretical part. Now here are the important thing, the Carmichael numbers. You remember that Fermat's little theorem says that a raised to power p minus 1 is congruent to 1 modulo p, where a and p should be co-prime. Now what happens here is that there are certain composite numbers like 561 which are composite, but still for each a which is co-prime to p, I'm considering as p. For each base that you choose a which is co-prime with p, Fermat's little theorem holds. Basically, any base you can choose which is co-prime to p will result into holding of Fermat's little theorem, and that is why each time when you run Fermat's test, in each iteration it is going to result into 1 if the chosen base is actually co-prime with p. In these type of for the Carmichael numbers, you have to be very, very lucky, and you have to choose a such that it is its GCD is not equal to 1. In only that case, Fermat's little theorem will not hold, otherwise it will hold. So these number are the ones which are actually a real challenge for Fermat's primality test. But good news is that these Carmichael numbers are actually very, very rare, and as you can see here, there are only 646 number up to 10 to the power 9. 646 Carmichael numbers up to 10 to the power 9. So these are very, very rare. So that is a positive news for us. Now, as I told you, we'll also be solving a problem. As you can see here, let me increase the font size. PON, prime or not from SPOJ. So the question is very simple. You are given t test cases. Test cases can be as large as 10 to the power 500. So each time you will be given an n which can be 64-bit integer, and you have to print yes or no depending upon whether the given number is prime or not. So we'll be solving this problem using Fermat's primality test. Now just a second, sorry, I have already solved this problem. One thing you should note down here, the time limit for this problem is 21 seconds, and the solution using Fermat's test that I submitted takes only 0.05 seconds. Let me show you the solution. Here you can see, just a second, increase the space. Here you can see I'm reading t, number of test cases, each time reading n, and calling the function is prime. If the number is prime, I'm printing yes, otherwise printing no. So the main function is clear. Let's go for is prime. Now is prime is actually the one which uses Fermat's primality test to test whether the given number n is actually prime or not. So I'm using 5 number of iterations. If n is less than or equals to 4, of course I'm taking care of base case, otherwise we are running a test for these many iterations. Each time I'm doing the exact thing, exact Fermat's primality test. Now the only special thing is here is this. Now bin power again uses binary exponentiation to calculate a raised to power n in log n time. And how I'm doing this, see, the number a can be as large as 2 to the power 63 minus 1, basically a 64-bit integer. If you multiply, this is, if you already know, this is binary exponentiation. Here you need to multiply result times a, and here you need to multiply a with a. Now if a and a both are 64-bit integer and they are almost on their range, if you multiply both, the result is going to be outside of the range of 64-bit integer, and in those cases you need to take care of that. Either you can use 128-bit integer using the boost library in C++. For Python user, this is not going to be a big deal, but for C++ user, if you are using 64-bit integer only, then a times a is going to result in overflow, 64-bit integer overflow, and you are going to get wrong answer, because the result is not going to be what you expected because of the overflow. Now to get around that condition, there is one other way to multiply two 64-bit integers using 64-bit integers. If you are calculating a times b modulo c, basically you are calculating modulo, then you can safely multiply two numbers a and b using the same approach that we using the same kind of technique that we use to calculate binary exponentiation. This is the exact same thing, and I'm using only 64-bit integer. LLI is long int, which is 64-bit integer, and multiplying those two using the same approach, same idea that we use for binary exponentiation, as you can see here. So you can read this code. I'll be providing the link of this code into the description of the video as well, so that you can read this and understand how I'm calculating a times b modulo c without getting integer overflow error. So this is how we are solving. We are doing nothing, just performing the basic Fermat's little test, Fermat's primality test, and we have got AC in 0.05 seconds. So this is how you solve this problem, and this is how you apply Fermat's little theorem. As you can see, this is very easy. All you have to do is calculate a raised to power p minus 1 modulo p each time, and that's all. So this was all for this lecture. Thank you guys for watching. If you have any doubts or query, of course you can ask me down in the comment section. So this was all for this lecture. Thank you guys for watching, and till the next video drops, keep coding. Thank you.